Hello, ladies and gentlemen, and welcome back. We've made it to the end of the year 2000 Euclid paper. That's right, we're on the last question, question number 10. And there's no parts to this one, it is a single question. An equilateral triangle, ABC, has side length 2. A square, PQRS, is such that P lies on AB, Q lies on BC, and R and S lie on AC as shown. Okay? So since they coincide with the line segment AC, we can see that PS and QR are going to have to be perpendicular to the line AC. Okay? The points P, Q, R, and S move so that P, Q, and R always remains on their side of the triangle. So Q is always going to be on BC, P is always on AB, and R is always on AC. And S moves from AC over to AB through the interior of the triangle. Okay. So the fact that they're saying through the interior triangle tells me that this is a process. This is a process, so we're going to get lots of these movements. If the points P, Q, R, and S always form the vertices of a square, show that the path traced, so the path traced by this process, out by S is a straight line parallel to BC. Okay. So P, Q, R, and S always form the vertices of a square. So what I think I'm understanding from this question, it's not really the best in terms of its wording, is we have a series of squares that always have one vertex on AB, one vertex on BC, and one vertex on AC. These are P, Q, R. And it's that fourth vertex, S, that it's moving. So we have a series of squares, and they're sort of rotating inside the triangle, but the square isn't fixed. It's sort of, I guess, the size of the square depends on where P, Q, and R are. But as we sort of shrink, rotate, and then enlarge again, this S sort of moves, and we're trying to show that it's parallel to BC, so it's at a sort of a constant height within the triangle. Okay, it's a constant distance from the line BC. Okay, I think that's what we've got here. So, if the points always form the vertices of a square, show that the path traced out by S is a straight line to BC. Okay. So, let's start by drawing ourselves a little bit of a picture. Get another piece of paper. And start by changing pen color to the black that we're accustomed to. So here's A, B, C, and we'll put the square in green, I guess. So this is the square as we currently have it. R, Q, and P. Okay. And then S is going to head this way. We want to show that it actually heads strictly on a line, so maybe we should use a little bit of an arc here. But if S is moving this way, then P will have to sort of move down this way, but I don't really know by how much. Q will have to move this way, and R will be moving up this way. So the whole thing kind of rotates, and we trace out the movement of S. And we want to show that this is parallel here. Okay. So an intermediate step here would be, so since this is a process, a good thing to do is to get a better understanding of the process, a good thing to do is to maybe draw some intermediate stages. So draw what it looks like at the start. What's it going to look like at the end? S is going to be completely on the side AB. What's it going to look like exactly in the middle, if you can find that? Q should lie directly below S, I guess. and then maybe a couple other intermediate stages, so you can really get a sense of what's going on, what the square looks like, how P, Q, R, and S are all moving. That's definitely a good thing to do. So I'm going to draw an intermediate stage right now. So we'll sort of just have moved. So S will be, I guess, around here. But R will still somehow be on A, B, C, A, B, C. So R will still be on AC, and get that. And Q will be down here, and I really don't have a very good picture going on right now. So maybe R is a little more here. Okay, but Q has moved a little bit further, and P is a little further down, and R is a little further up, is the idea. And we'll say that this has, well, first let's clear up the picture a little bit, because I have a couple stray lines. Okay. We get out our green. Okay, and so S should be sort of moving along this dashed line that is parallel to BC. We don't know that. That's what we want to prove. And so we'll say that this is, we sort of moved out a little bit by angle theta. Okay? So why did I choose theta? Okay? Well, the reasoning behind this is P, Q, and R are all moving. Okay, S is moving as well, but P, Q, and R are sort of sliding around along their sides. Now, we could say, oh, maybe what we could actually do, knowing that ABC has a side length of 2, we could actually probably start figuring out like the length of that original square and the positions of P, Q, and R. And we could even go so far as to maybe even introduce coordinates. And so what we could do is we could say, well, P is sliding down towards B, and it has moved length P. Okay? And figure out where Q must then be, and R must then be, and then S must be. Okay, and maybe work through it like that, because the movement of Q depends on the movement of P, and knowing that we have to create a square. So that's certainly possible. But if I'm going to do that, if I'm going to base everything on how far P has slid, then I'm likely going to have to start talking about angles. I'm going to have to start using the cosine law to figure out the length of this new square, and how far Q has now slid, how far R has now slid, and where exactly S should be. So I'm going to have to start getting angles involved somehow. I'm going to be using the sine and cosine laws most likely to figure things out. And so, faced with that option, or picking an angle and saying, oh, the square has sort of rotated by that angle, I choose the second option, because otherwise then we're talking about, I'd say it's easier to talk about lengths in terms of angles. You know, the height of the triangle is the one side times the sine of this angle, as it is, and it's much harder to talk about angles in terms of lengths, because then you have to sort of reverse engineer the cosine law and use an arc cos and things like that. And I don't like using arc coses in my formulas if I can help it. So I'd like to talk about angles as much as possible and derive the sides from them, as opposed to talk about sides and derive angles from them to compute the rest of the positions of where S is and how long the square is, or what the side length of the square is. So that's just my preference, and that's what I'm starting off with right here. I don't know if it's going to work out, but based on my understanding that the square sort of shrink rotates, I think picking the angle of rotation is probably the best way to go. Okay? So, go back to our picture. I've given this guy the name, actually I don't like theta, I'm going to go with sigma. I think I prefer sigma. I think it's much smaller, much more compact. I find I'm a little messy when it comes to my thetas. So we're going to call that angle theta. Okay. So up here, sorry, theta, geez, I really need to pick sigma. This is sigma. Sigma, 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 sigma. You guys can use theta if you want. So up here, sigma would be 0 degrees. Okay. Now we know that it's an equilateral triangle, so we have 60 degrees here, and we have 60 degrees up here, and we have 60 degrees up here. And we know that this in total should be 180 degrees. So this is going to be sigma plus 90, all subtracted from 180. This angle right here is 90 degrees minus sigma. Combining that with this 60 degrees, we can fill in this triangle, QRC. And we can see that this guy right here, he's going to be 30 degrees, right? 30 degrees plus sigma. And then this one over here, that'll be 60 minus sigma. And this will be 60 degrees plus sigma. Okay. So now we've got some angles in here. And we do know that we have a side length of 2. So we could probably start using the side length of 2 to get some lengths. But I don't know if I want to do that yet. What I'd really like to do is, because we're talking about the movement of S, I would like to maybe at least draw a picture where I can talk about, in terms of sigma, where S is, how far away from BC S is. Because if we can show that regardless of how far we've rotated, regardless of what sigma we're talking about, what angle sigma we have, that S is a constant height away from BC, a constant distance away from BC, then we'll be able to show that, yes, S traces out a parallel line. So, let's, on our picture, or maybe because this one's a little cluttered, draw ourselves a way to figure out where S is. A way to figure out how far S is from BC. Because if we can show that's constant, then we're all set. So, I'm just going to redraw the picture a little bit. Actually, let's go for broke and draw a giant copy of this thing that maybe we'll have to refer back to. So A, B, C, and that nearly worked. I don't know what it is. I can't seem to draw an angle right now. Let's start from here and work. Alright, that worked out a little better. So there's S. We'll fill in this side. Okay, here's theta. And Q always lies on BC, so maybe we can drop. We want to talk about this length right here. QS is a diagonal of our square here. So if we can figure out the side length of the square based on terms of sigma, which I have to believe we can, we'll definitely get this hypotenuse here. And then that's going to be 45 degrees plus 30 plus sigma. So the whole thing, that whole angle is going to be 75 plus sigma degrees. we're going to have to start writing this up. Picture drawing can only go so far. We'll call this point D. Okay. SD is going to be QS times the sine of 75 plus sigma. Okay? So if we can figure out QS and we can figure out that out in terms of sigma, maybe the sigmas will cancel out and we'll find that SD has a constant height. But let's get to writing some things up. Okay. So let's let D be the point on BC so that SD is perpendicular to BC. We're going to let sigma be the angle of ARS. As sigma increases, our square changes, and S moves, as per the question. So we start with sigma equals 0 degrees, and S will reach the side AB when sigma equals 30 degrees. Okay. If we can show that SD is constant, regardless of what angle sigma we rotated by, we'll have shown S moves in a line parallel to BC, and that's exactly what we wanted to show, correct? Show the path traced out by S is a straight line parallel to BC. Okay. So now we've got something that we could maybe talk about. All right. So we want to show that S just sort of moves across a line. Well, if we can show that SD is at a fixed distance, is constant, regardless of the sigma, regardless of how we're rotating our square here, then we'll be all set. Okay. Now the question is, how do we figure out how do we figure out what SD is in terms of sigma? So let's notice that SD, we're just writing what we had before. SD is SQ sine 75 plus sigma. Since triangle SDQ is right angled. Okay. So if we can just figure out SQ in terms of in terms of sigma, we can plug that in and hopefully everything will cancel out. I'm seeing that we're probably going to have to use a bunch of sines and coses of something plus sigma. So already in my mind, I'm starting to try and remember, okay, what is the double angle formula? What is the cos of a plus b? What is the sine of a plus b? What is the sine of a minus b? And so on. These are formulas that we should know, and if they get brought up, then we're going to be using them. Okay? But already I think that sort of thing is going to pop out. Okay. So what do we know? Okay. Well, let's go back and look at our picture. I don't want to draw it out for a fourth time if I can help it. All right. Let's add in the points P and R. Okay. So, we know we have a given angle of 60 degrees here. And these other angles, and this angle over here is 60 degrees at C, but the other angles, the angle at P, the angle at Q, the other angle at Q, and the angle at R, are all in terms of sigma. 90 minus sigma, 30 plus sigma, 60 minus sigma, and 60 plus sigma. Now, these common side lengths here, or sorry, the side lengths of the square, are both opposite the 60 degrees. Okay? So I think we could use the sine law. So let's recall triangle BPQ and triangle CRQ. So they look like this. Q, R, P, and we have B and C. And we have 90 minus sigma, 30 plus sigma, 60, 60, 60 plus sigma, and 60 minus sigma. So we're going to let x be the side length of the square. Okay? So since SQ is a diagonal, SQ, it's not that hard to see, SQ is going to be square root of 2 times x. Okay? So if we can work out what x is, we'll have a better understanding of what SQ is. Alright. So in triangle BPQ, the sine law tells us that x over sine 60, which is a constant that many of you should know. Sine 60 is the square root of 3 over 2. Many of the basic sine and coses you should know. Sine 30 degrees, cos 30 degrees, sine 60 degrees, cos 45 degrees. 30, 45, and 60 degrees are sort of the special ones that you should know. If you want to add to that list, I guess 75 and 15 are the next ones to know, but I don't even know those off the top of my head. But you should know sine 60 is root 3 over 2. You should know cos 30 is root 3 over 2. You should know sine 30 is 1/2, things like that. Okay, so we can start working these constants in here. Although, for all I know, we might just be able to leave this the way it is. But we have x over sine 60 degrees. And what I'm going to do is I'm also going to get it in terms of these lengths here, which I will define as, we'll put these x's in blues. I'll call this B and this C. And the reason I'm going after these lengths here is because they add up to a constant value. I know what that value is. I was told in the question that the side length BC is 2. So little b plus little c, that should be 2. Okay? So little b over, and now we're at sine 60 plus sigma. And so applying the sine law in the exact same way in CRQ, we once again have s over sine 60 degrees because x over sine 60 degrees because x was opposite the 60 degrees is equal to c over the angle that it's opposite, which is 90 minus sigma. Okay? So we also know that b plus c is equal to 2. So if we rearrange these equations, well, if I can get c in terms of x and I can get b in terms of x, then I can add those two together, and then I'll get constant number 2 in terms of x, and hopefully I can solve for x. And that'll be in terms of a bunch of angles like sine 60 degrees, but also in terms of things like sine 90 minus sigma. So we get b is going to be x over sine 60, and that'll be, didn't leave enough space here, so it'll be x over sine 60 times sine 60 plus sigma. C will be x over sine 60 times, we rearrange this, sine 90 minus sigma. Okay? So now we can see 2 is going to be equal to, we'll get sine 60 plus sigma plus sine 90 minus sigma all over sine 60 degrees. I'm going to leave this in as long as possible, see if the 60 actually matters, times x. Okay? So that means that x is going to be equal to, well, we flip this and multiply it by 2. So sine 60 degrees times 2. I should rearrange that and say 2 sine 60 degrees. And this will be sine 60 plus sigma plus sine 90 minus sigma. Okay, so we achieved one of our goals. We now have x in terms of that angle sigma. Okay, and sigma starts at 0, it goes all the way to 30, and so s passes from AC onto AB, and we think that should be a straight line. Now all we have to do is compute SD in terms of sigma and show that the sigma doesn't really contribute to the calculation. So we should get a bunch of cancellations. And as I predicted, I think we're going to have to use the sine sum angle formulas. Okay? So this should now boil down to a lengthy computation, and that should be it. So we just need to show that SD, which is square root 2x sine of 75 plus sigma. So now let's start putting things in. So if we plug in for x, we get 2 root 2 sine 60 sine 75 plus sigma all over sine 60 plus sigma. plus sine 90 minus sigma. Okay. So I want to get a constant out of here. What can I do? What can I do? Well, I don't need this 2 and this root 2. Those guys are just cluttering things up. And sine 60, that's already a constant. So what I need to do is show that what's left over, everything involving sigma, happens to sort of cancel out in some way and become a constant value. By the way, if you wanted to, I'm not going to because I think I'm on the right track, but if you were a little suspicious, maybe you calculated something wrong, that's habit. You second guess yourself all the time. You could say, okay, this expression needs to be a constant regardless of what sigma I put in there. So what you could do is grab your calculator, and it's a fairly straightforward expression, not too difficult. You could plug in sine of, and then you could plug in sigma equals 0 and see what you get, and sigma equals 20 and see what you get with this expression, and sigma equals 30, or sigma equals 5, or sigma equals 7, or something like that. You could test a couple sigma values to make sure that this actually does turn out to be a constant, that we haven't made a mistake somewhere, we're not in error in our method for thinking about things. So, if I were unsure, if I were a little nervous, and if I had the time, what I would do is I would take some random sigma values in our range from 0 to 30, and I would test this expression and see, is it actually a constant? Because if it is constant with some random sigmas thrown in there, then I should be able to show that, but at least I'll know I'm on the right track. And you could always, if you run out of time, say, here's what it is I did this with calculator, here's what it is with sigma 0, sigma is 20, sigma is 7. So I know this is constant, I just didn't have time to show that. And you can still get some part marks and show that you were at least using some reasoning. So we need to show that that is our constant. Okay, and now we're going to have to use the angle sum formulas. So sine of A plus B is equal to, it's sine A cos B plus cos A sine B. And then because we have that 90 minus sigma in there, we should also write out the A minus B version, which is sine A cos B. I wasn't saying, oh geez, because I couldn't remember, because obviously you can easily remember this. I'm trying to remember which one the minus goes in front of, but B is the one that changed to a minus. And so B has to be the one that's a sign in the second expression. Okay? Because cos A and cos negative A are the same, but sine is the one that flips sine when you change to a negative angle. Okay, so we're going to use these guys here. And it's good that we have a bunch of white space because we might be backtracking in our calculations and we might have some very lengthy ones. So this is a sum here, but do I want to break it up into 75 and sigma? Okay? It may turn out that I have to do that. It might be the case. But I don't really want to. I'm hesitant to. I think I actually will, but I'm hesitant to because it could break up so much more easily into sine of 45 and sine of 30 plus sigma and things like that. But I think I'll try 75 plus sigma and see what happens. Sine of 60 plus sigma But see, then this one becomes sine of 30 and 30 plus sigma. And that's so nice. And this one, 90 minus sigma, how could we get a 30 plus sigma there? We do 120 minus 30 plus sigma, I guess. Yeah, I don't think I'm going to split it up into 75 plus sigma. I think I'm going to do this. Sine of 45 plus 30 plus sigma. I'm going to get a whole bunch of 30 plus sigmas in here. It may not end up making a difference, but I think it will. $30 plus sigma plus sine, and now we have 120 minus 30 plus sigma. Okay. And so that's going to be sine 45, which I don't care about, cos 30 plus sigma, plus cos 45, which again is a constant, it's 1 over root 2, sine 30 plus sigma. So now I have some 30 plus sigmas. I guess I can't really take it out. But these two numbers, sine 45 and cos 45, are the same value. They're both 1 over root 2. So really what I have on the top here is some constant times cos 30 plus theta plus sine 30 plus theta. Okay? And on the bottom, what do we have? Sine 30 cos 30 plus sigma plus sine plus cos 30 sine 30 plus sigma plus sine 120 cos 30 plus sigma minus cos 120 sine 30 plus sigma. Okay. So both of these are 1 over root 2, so 1 over root 2 cos 30 plus sigma plus sine 30 plus sigma. And then cleaning things up on the bottom, we need to group things together. So the cos 30 plus sigmas, we're going to group them together, and that's sine 30 plus sine 120 cos 30 plus sigma plus cos 30 minus negative cos 120 sine 30 plus sigma. And that should be multiplied. I'm going to rewrite that a little bit, just so it's clear that they're being multiplied. So all we've done is we took out the constant on the top and we collected like terms on the bottom. So we have cos 30 minus cos 120 sine 30 plus sigma. Okay. So we can still have the 1 over root 2 at the top. But now, sine 30 is one of those angles we should know it's 1/2. Sine 120, that's another one of those angles we should know it's root 3 over 2. Okay, and I think this will end up being the same expression. So cos 30, that's root 3 over 2. Minus cos 120. Once you are over 90, the cosine becomes negative, so that should be negative 1/2. Sine 30 plus sigma. And so these negatives cancel out, and so both of these are going to be 1/2 plus root 3 over 2. That's 1 over root 2 cos 30 plus sigma plus sine 30 plus sigma all over 1/2 plus root 3 over 2 cos 30 plus sigma plus sine 30 plus sigma. And rather happily, these guys cancel out. And we get a 1 plus root 3 on the bottom, and then a 2 goes up to the top. So it should be root 2 over 1 plus 3. So SD was 2 root 2, I think, times this constant. Well, let's just double check. Yeah, 2 root 2 sine 60 times this constant. So we have to throw in the sine 60 degrees here. Sine 60 degrees, that's root 3 over 2 times root 2 over 1 plus root 3. And those two will cancel out. Those two will cancel out. So we should get 2 root 3 over 1 plus root 3. But the real important thing is that SD is a constant with respect to sigma. Because this is constant, regardless of how we've rotated that square, as we've already remarked, that means that S, as it's moving, no matter where it is, it must be at a fixed distance from BC, and that means that S traces out a parallel line exactly as we wanted to show. Okay? Exactly what we wanted to show. So we've gone through the question. We just double check, show it's a straight line parallel to BC. Well, that's exactly what we managed to do. And that's it. We're done the year 2000 Euclid paper. That was question number 10. A very nice little question indeed. A couple things that I'm wondering about. What if I hadn't chosen to use the angle at the start? What would have happened if I had said, well, let's nudge P by a given amount? And would the question have been easier, more difficult? I thought it was fairly straightforward the way we did it. And my last minute change of splitting sine 75 plus sigma into sine 45 plus 30 plus sigma wouldn't really have mattered if I had just done our sum angle formula on sine 75 plus sigma as is. That's another thing I'm wondering. So leave a comment if that's something that you tried when you did this contest. And if you're looking for more of these contests, you can find more Euclids by clicking the link in the description. You can find simpler contests because it just takes you to the University of Waterloo pages. And if you're interested in more Euclid videos, I'll be posting more as soon as I make them. So feel free to subscribe to keep up to date, and I'll see you guys on the next contest, whatever it is.